Morning. So we'll talk about random variables and distribution. The practical questions are not yet ready on probability. I was busy this week, so I couldn't come up with the questions. We'll have the practical class in the coming Tuesday. Okay, we'll talk about random variables and distribution. Now, we are somewhat familiar with the and the concept called as variable. Variable is a quantitative characteristic which varies from place to place and time to time. And this variable of interest could be any characteristic like height, weight, mass, number of defectives, uh, any particular rate value, growth value, etc. So that could be the variable. Now, if we have a variable, we know how to extract the data, how the data can be grouped into various cases like discrete frequency distribution, continuous frequency distribution. Similarly, in the field of statistics, we come across with a set of random variables, a set of variables which are special, and they have their association with respect to sample space as well as the probability. Now, we have learned how to obtain the probability for various events. Could be either the empirical approach or the classical approach, but the probabilities can be computed. If I want to have a probability distribution, please turn off the videos there. ಯಾರದು ಮಹಿಮಾ ವಿಡಿಯೋ ಆನ್ ಆಗ್ಬಿಟ್ಟಿದೆ ನೋಡಿ. So if I have the set of values which I call as probability, and if I want to have a distribution of probabilities for the various events, but if I want to look into the behavioral properties of the distribution like mean or variance or any other measure, then I need the real values for the elements or the events. So we have to somehow bring the concept of variable into the field of this probability. So what we define is we have come across a simple statement which we call as function, a mathematical function from sample space to real life. So use a function which we generally call as random variable or function, that is a function defined on sample space which converts every elements of the sample space into real numbers. Now when we are converting elements into real number, now you know that set of elements is nothing but an event, and every element is nothing but a simple event here. So events are also categorized into or converted into real numbers. So you have a real number, say under the variable x, and since event is converted into real number, now the event can be replaced by that real number quantity, which is function, and we call that as probability of the variable instead of calling it as probability of event. So it is very much simple. We are breaking the events into very simple cases with respect to one or more element, and that element is being converted into a real number by defining a mathematical function on that, and that mathematical function is called as random variable. Why is it called as random variable? Because of the random nature of the outcome. Every statistical experiment has several possible outcomes, and each of the possible outcome is random. Whenever you are taking a trial, you are conducting the experiment, you know what are all the possible values of outcomes, but specifically for that trial, you fail to mention that. So that's why I say it as any one out of those possible cases. So we have our x and we have px. So the distribution of the values taken by the random variable along with the probabilities are called as probability distribution. So two important definitions are learned here. What is a random variable? A random variable is a function from sample space to real life. Random variable is a function from sample space to real life. Let me take an example. So we are talking about experiment of tossing two coins, and we know the individual probabilities. If I take the events as say E1, E2, E3, E4, where every event is defining a particular outcome on the experiment, say observing both heads, observing heads first, observing heads at the last, observing no heads or both tails. These are the events. And if I look into the probability of my E1, it is 1 out of 4. Okay, so E1 is nothing but getting both heads. So the favorable outcome for E1 is just HH. So if you look into your M, which is N of E1, that is equal to 1, your N of S has 4 outcomes. Therefore, by classical definition, P of E1 is M by N or N of E1 by N of S, which is 1 by 2. Since I have taken only one element on these events, so I observe all the probabilities E2, E3, E4 for the events. The probabilities are 1 by 4 only. So I have the probabilities for every element of the sample space. Now I have to convert this sample space into a real number. So I should obtain numerical values which can represent or replace these particular notations, and that function is called as random variable. So here many different ways are there, but the most commonly and easily understandable function is x is equal to number of heads. So we are conducting the experiment. Instead of looking into the particular outcomes, we look into the outcomes and we count how many heads are observed there. Now, if I say how many heads are observed when I have the outcome as both heads, that is x is equal to 2. If I take number of heads in this case, so I have got head in the first coin, tail in the second coin. So whenever this outcome has happened, then the number of heads observed is 1. Again, in this case, number of heads observed is 1. Number of heads observed, no heads observed, therefore it is 0. So our sample space is now converted into real number, where this experiment of tossing a coin, tossing two coins, and we are counting number of heads. Now similarly, you can define x as counting number of tails. So in that case, this will be 0, 1, 1, 2. So these are the two most commonly used definition of x for this particular experiment. So if you see that whenever you toss two coins and you are counting a particular case of head or tail, it ranges from 0 to 2. Now you can extend this to 3 coins, 4 coins, and so on. And then you can easily obtain the probabilities also. So we in the last class observed that writing the sample space is easier for the case where we talk about 2 coins or 3 coins or at the most 4 coins. But when the number of coins gets increases, writing the sample space becomes tedious because number of elements in the sample space will be 2 power 5 for coins, 2 power 6 for 6 coins, 2 power 10 for 10 coins. But our probabilities are based on what is the number of elements in the sample space. So if I just know that, and if I know what are the favorable cases for a particular event, in that case probabilities could be easily obtained for the values of x rather than the outcomes of the experiments. It's one and the same because your x is nothing but a particular outcome. Now let us just put a condition on this. X function x is from sample space to real number. So if you have a set of elements in the sample space, we define the function such that two or more elements can be mapped into a same real number, but no two real number will be mapped into same particular outcome. Okay, what I'm telling is you can have a situation where two or more elements of the sample space is taking the same real number, but two or more real numbers cannot take two different, the same particular outcome. Two real numbers cannot take the particular outcome. So this inverse mapping should be such that it is just one. So this condition is satisfied, then only we call that function x as a random variable. So you need not worry about deep mathematical concepts there. So just remember x is a function from sample space to real number, and we define x, and for x we compute the probability. Now how to compute the probability? So we have probability of HH, HT, TH and DT known. So we'll write that as x. And now instead of calling the probabilities as P of E1, P of E2, now E1, E2 are basically the simple elements of the sample space. Now those are represented by the symbol or the variable x. So we'll talk about P of x rather than calling it as P of E1, P of E2 when we are talking about probability distribution. And to be precise, we are observing that our x is taking several values 0, 1, 2 and so on. And generally, we use the small letter x to indicate the values taken by the random variable. Values taken by random variable, and this is our random variable. So if I have three values taken by the random variable, say x1, x2, x3, then the distribution of this x1, x2, x3 is simply given in the general form like this. So if my random variable is taking only these three values, then the first probability, that is, what is the chance that my random variable will take this particular value x1. So that is indicated by P of x is equal to x1, or simply you can say P of x1. So this is similarly P of x equals x2 or P x2. This is P of x is equal to x3 or Px. Now if you observe, your x values are exhausting the sample space. All possible outcomes are converted into x. So these are the only possibilities. And if you look into the probabilities, whenever you have computed the probabilities for each and every element of the sample space, and if you look into the total probability will be always 1, because you're talking about a case where every event is disjoint there, and if you obtain the union, you'll get back your S. Therefore, the total probability will be equal to 1. Now, each and every element is converted into x, and if you look into the probabilities for all the values of x, so there also you will observe that the total probability is equal to 1. So, under all values of x. So, this happens for all the probability distributions, and as we have the concept of continuous frequency distribution, discrete frequency distribution, the same can be extended to the random variables also. You can have a random variable where you have a discrete random variable or a continuous random variable. Now let us see how to write this probability distribution for the example where I have sample space S as tossing the 2 coins. Okay, so this has been mapped into x is equal to 0, 1, 2. So these are the only 3 possible values taken by x when I define x is equal to number of heads when 2 coins are tossed. Now we have to come up with the probabilities. Okay, so listen here. x is equal to 0 happens when your outcome is HH. So if your outcome is HH, only then you can observe 0. So if I say P of x is equal to 0, it is actually what is the probability of observing both heads, and it is 1 out of 4 case, therefore it is 1 by 4. So here we write P of x is equal to 0 or P of 0 is equal to 1 by 4. Next, your 1 can happen in two ways. So if your result is HT or TH, result is HT or TH, in that case, you can have x is equal to 1. So P of x is equal to 1 indicates P of observing one head in the form of HT or TH. Now, if you look into HT or TH, both are disjoint. Disjoint in the sense they cannot happen together when you conduct the experiment. So whenever you take a trial, either HT happens or TH happens. So that's why we have written OR, and OR, mathematically indicates union. And while defining the axiomatic probability, we said if A and B are two disjoint events, then their probability of union will be same as probability of sum. So this is simply P of HT plus P of TH. So P of HT is 1 by 4, P of TH is 1 by 4. Therefore, it is 2 by 4, which comes to half. So we write P of x is equal to 1 or P1 is equal to 2 by 4. And the next case is observing, okay, let's say that one. So this is 0 heads is TT, and then 2 heads is HH. So that is P of x is equal to 2. Again, one case out of 4. Therefore, the probability is 1 by 4. Now, if you look into the total probability, total Px, that is equal to 1 plus 2 plus 1, which is 4 by 4, that is equal to 1. So if you're talking about any probability distribution of a discrete variable such that the total probability is coming to 1, then that distribution, probability distribution, is called as PMF. Is called as PMF, which is probability mass function. So that's an important definition here. You could ask, what is probability mass function? Probability mass function is simply the probability distribution of a discrete random variable such that the total probability is equal to 1. If the total probability is not equal to 1, then you are just observing the probability distribution. It cannot be called as PMF. Now here we are using the concept of sample space and simple, experiments and examples just to understand the distribution. But in more general, you can have the variable, where it is, directly imagining the sample space would be difficult. And moreover, as said, we'll be using the past data to come up with the values of x as well as the probabilities. Now, the other way to consider distribution is based on the statistical approach, which is the relative frequency approach. So here we used sample space, and we are telling that whenever you toss 2 coins once, probability that you will get both heads is 25%. Or probability that you will get one head is 50%. Or probability that you will get no head is 25%. But that is not so, because if it is, if I say it is 25%, that means that if you take 4 trials, then out of those 4, in one case you have to necessarily observe 2 heads. But that might not happen in the real life. Say if you toss 2 coins even for 10 times or 20 times, you might fail to observe HH, and you could get all the 20 trials to be one of these cases. So in that case, those probability techniques fail. But when you conduct the experiment in a large number of cases, the result will definitely hold forth, provided the coin is an unbiased coin. Unbiased in the sense it produces equal number of heads and tails whenever it is tossed for a large number of cases. In the cases where you don't want to obtain the probabilities using the sample space, or you have a belief that the coin is not a unbiased coin, it is somewhat biased, it doesn't produce, or the events are not equally likely. So whenever we say coin is unbiased, the events are not equally likely. Not equally likely in the sense there is no equal preference for these possible outcomes. The coin favors a particular outcome. Now the coin is biased, or a little weight is added on a particular side, such that whenever we toss, only tail will come. So such coins are called as biased coins. So in that case, if you want to look into what is the probability of observing various such cases, then again we have our x values as say 0, 1, 2. Now let me take the experiment in terms of number of tails. So we are tossing two coins and we are observing how many times we observe the tails. Now to obtain the probabilities, what we do is we toss this coin, let me say 100 times. So we are applying the statistical or the experimental approach of finding the probability. So toss these two coins 100 times. So that is what the definition, right? Any probability of event is limit n tends to infinity m by n, where you are conducting the experiment for a large number of times, say n, and out of n times, you are counting how many times your favorable outcome is observed, which is our E event. Okay, so I'll toss the coin 100 times, and every time I'll see the result, and I'll prepare a frequency distribution for the number of tails observed. Okay, so totally I'm conducting the experiment. I'm taking the trials, 100 trials. Now, in the first time, I have got 0 tails. In the second trial, I have got 2 tails. In the third trial, I have got 0 trials. So, every time you will observe what is the outcome. So, you'll use the tallies and you'll come up with the frequencies. Now, let me say out of this 100 tosses, I have got no tails for 10 cases. I have got one tail for say 85 cases, and the remaining 5 cases I observed both the tails. So this is the frequency. Now if you want a particular probability, now the probability is just the ratio m by n. Now what is the probability that my x is taking the value x? So what is the probability of x is equal to 0? The definition says how many times you have observed 0 divided by how many times you have conducted the experiment. So it is 10 out of 100 times, which is nothing but the relative frequency. So you are computing relative frequency, and whenever your n is very large, in that case, the relative frequency, talking about this cell, the relative frequency can be easily taken to be probabilities. Now, this biased coin is such that it produces 85% of times one head or one tail. So, if you are talking about a competitive situation where the person is uh, tricking you by paying by exacting some amount, so he says toss two coins. If you observe the same outcome, I'll double your money. Then you should first actually see what are the actual probabilities, what type of coin is using, is it an unbiased coin, is it a biased coin, and if there is a chance you could observe the trials taken by him, look into some counts, how many times he did the experiment, what is the most likely outcome in the particular experiment, compute the probabilities, and then take the decision. So here both the distributions are probability distributions, both are PMF because the total probability is coming to 1, and then both are very much discrete in nature because you are identifying the particular values. So if you remember, two types of variables, discrete variable and continuous variable. Discrete variable is the variable which takes only some specific values in the interval, whereas continuous variable can take any or all possible values in the interval. So if I have given a range for x, say my x belongs to somewhat 5 to 10, and if I could say my x takes particularly 5 or 5.5 or 6 or maybe 10. So only these four values and nothing else. So whenever you conduct the experiment, you are observing only these cases. In that case, we say x is discrete. Now you are in a situation where if you say x belong to this, but my x can take any value 25, 5.6, 6.99, 7.98, 8, 10, etc. So you cannot specifically say in that case it is continuous. Okay. So the continuous concept mathematically it is such that you cannot actually quantify a particular value. You cannot guaranteely say it is 5.25, but you are using the tools or machines such that you could measure up to the first two digits or first three digits only. But in reality, in nature, that particular variable cannot be quantified by a single number, and never ever you will observe the persons with same values of x when you're talking about a discrete nature. Let me support my statement. So if we're talking about weight, if I ask you what is your weight, you cannot exactly tell the weight. So it might be 53.5 kgs. So last time when I measured it is 53.5 kgs. Okay, now measure your weight now. You can measure it maybe up to two digits or maybe up to one digit. The machine or the weighing scale is adjusted such that it produces an approximate number close to your weight, but your real weight is any number which is not possible to capture. So we have techniques, tools, which helps in observing some, decimal digits only, but the entire thing is not possible. So whenever we talk about the concepts like say height, weight, or any continuous random variable, we are talking about a number which is, the observed number or the observation is such that it is close to the actual value. That is the major difference between a discrete variable and a continuous variable. Now, even in the field of random variables, you can have discrete and continuous. Now, these height, weight are also the random variables because you are selecting the person randomly and you are extracting the weight. So, if I define x is equal to weight of a randomly selected student, then x becomes a random variable and it is a continuous random variable. And whenever we have a continuous random variable, you cannot come up with a frequency distribution by writing each and every value of x, because your observed value could be just one in number. So if you have extracted some data on weight, as said, you could observe 53.6, maybe 58.2. So very rarely you will observe the repetition. So it is impossible to write each and every value. In that case, again, we look into the probability, the conception of the class intervals, or, the shorter subranges. So you divide your entire range of data into sub-ranges, maybe say 50 to 60, 60 to 70, 70 to 80, and so on. And for that, you will compute the frequencies. In the same way, we construct the probability distribution. Now, if I say what is the probability for this particular x, so here it is not for a particular value of x, because here my x is from 50 to 60. So in this case, the probability is defined as probability that x is lying in between 50 and 60. So when we are talking about a continuous random variable, you cannot talk about probability of x is equal to a particular value t, because that is very rare to observe, and capture. What are all the values you are capturing? They are just the approximate values for that particular case. Therefore, capturing exact value becomes the probability 0, and this happens for all continuous distributions. Hence, for continuous distributions, you can obtain probabilities only for a small range like this. What is the chance that the weight is in between 50 and 60? Or what is the chance that the student marks is in between 60 and 70? Or even if you're talking about an interval, say open-end case, and what is the chance or probability that my x is taking the value greater than 80? Now, how do we come across, such probabilities? Again, use the statistical definition. So you know the frequency distribution of weight. Convert the frequency distribution into relative frequency distribution. Relative frequencies are probabilities. So you can easily obtain the probabilities. Now we'll have the sketch also, the sketch of PMF and PDF. The continuous distribution functions, they are called as PDF. So let me first define this PMF PDF correctly. PMF, probability mass function. A discrete random variable x is said to have a PMF. A discrete random variable x is said to have a PMF if its probability function or probability distribution is such that, first one, p of x is greater than or equal to 0 for all x belonging to x, and second one, total probability for all values of x will be equal to 1. So this is the mathematical definition. So what are we telling here is, we are just applying the already known conditions on the probabilities. While defining probability, we said probability of any event is such that it is always greater than or equal to 0. But since it is the chance in terms of percentage, at the most our A could be equal to sample space, and we already know that our probability for any event lies between 0 and 1. So this, need not be hard and fast rule. In every such random variable, will observe probability be greater than or equal to 0 for particular cases of x. But what is the required condition is that if you have obtained the probabilities for all possible values of x, and if you compute the total probability, that should come to 1, then our function px is called as PMF. So this px is our probability function. Why is it called as probability function? That will be clear in the next set of topics. Right now, we'll just take it as a mathematical function. So here, in the example what I gave, I have just written you the particular values. So I had the column P of x is equal to x. It was 1 by 4, 2 by 4, 3 by 4. But this could be, these values can be given by a mathematical form, mathematical function, which produces these values 1 by 4, 2 by 4, 3 by 4 when I specify the values of x. So you can come up with a formula which produces this, and that formula is simply P of x is equal to x, called as probability function. How to come up with that formula, that we'll discuss in the next class. So this is how a probability mass function is defined. And the reason why it is called as mass function, mass, because you are observing the probabilities for particular values of x. So you can come up with a probability for discrete particular values of x. And if you obtain the graph for this, or the histogram for this, which is your x values on the x-axis and P of x on the y-axis. So the same as obtaining the histogram for a continuous case, but here, since you're talking about discrete nature and not for a class interval, your rectangles are nothing but straight lines. erected such that you have the probabilities of say height 1 by 4, 2 by 4 and 1 by 4. So this is called as sketch of PMF. So you can see the height of the line is actually equal to the probabilities. So the concept of height is the probability when you're talking about sketch, and this is called as the graph of the PMF. So if you have very much different and many possible values of x, you could erect straight line such that the height is representing the probability, and this happens in a case of discrete random variable. Now, when we talk about a continuous random variable, there the probability function is not called as mass function, but the concept of area comes into picture. That is the concept of density. So, no more the height will be equal to probability. The set of rules how we define probability, they only change. So here we are talking about particular case. There is no particular case, so you cannot find probabilities for each and every value of x, but you can find the probability for a set of values or a group of values of x, like in between 2 points, more than a particular value. What is the probability that it is less than a particular value? So when you talk about somewhat called as the sub-range, then we are talking about the concept called as a continuous random variable. In that case, the density function or the probability function is called as PDF. It's called as PDF, and our probability density function could be such that this condition need not be satisfied, or we indicate it by f of x precisely, but is said to have a PDF if its probability function. Now we are indicating the probability function by f of x. You can use still p of x, but the definition of p of x becomes very much different. So here we are talking about area, and when we talk about area for a function, the areas are obtained by the technique of integration. So we apply the condition that integration of f of x dx over all possible values of x, which I call as range of x, is equal to 1. In that case, that f of x is called as PDF or probability density function. Now, if you look into the sketch of this for various cases, let me say you're talking about the graph of a continuous distribution. So you'll have the shape like histogram for various cases. So you have say 50 to 60, probability is 0.5, 60 to 70, it is 0.8, and so on. So this is what is happening, but in more general form. So if you keep on reduce the size of the interval, you will get more smaller rectangles, which makes the shape somewhat smoother and smoother like this, and you could end up get a still finer function which produces a function like this. So here